Welcome to Scary Programming Terms. In this episode, we're going to talk about abstract syntax trees. It's a pretty frightening sounding phrase, and people who talk about it tend to be compiler engineers and people writing interpreters, which makes it seem extra scary. But it's actually a really simple idea, and it's really simple to implement one as well. So you'll often see this abbreviated as AST as well when people talk about it. So what is it? So when we want to make something like a compiler or an interpreter or our own programming language, you're going to start with some kind of source code, some text, and then magic's going to happen, right? And you end up with an executable eventually. So various steps can happen in here, like parsing and outputting machine instructions and so on. But usually, somewhere in the middle, you will have an abstract syntax tree. And what it is a representation of your program in the form of a tree. Right? And so if you're familiar with binary trees from any intro to programming course, pretty much everyone is pretty comfortable with these. Right, a binary tree has nodes. Each node has two children. And these can be useful for a variety of things, right? If you put numbers in them in order, right? So you put some number in, and then any number less than this node goes to the left, any number greater than goes to the right. Then you can do useful things, like you can find a thing in log n time, because you only have to search the height of the tree to find something. You can output things in sorted order by doing an in-order walk of the tree, where you visit all the left nodes, print out the current node, then visit the right nodes. So these are very handy, and most people understand these fine. And so an abstract syntax tree is just the same thing. It's a tree. It does not necessarily have two children for every node. It could have any number of children. So an abstract syntax tree might have one child in some cases. It might have 4 children in other cases. And these trees somehow represent what your source code is saying should happen in your program. So how do we do that? How does that actually work? So let's take a really simple language. We're just going to talk about equations. Equations that can have constants and will allow for a single variable x. So we can have equations in terms of x. So let's just do a really simple one. We'll do 2 plus 1 minus x. And we'll put this in parentheses to make order of operations clear. So 2 plus 1 minus x, how does that get represented as a tree? Well, we'll start out by breaking things into pieces. So every element of this equation can be a type of node. So we'll have a plus operation, a minus operation. We'll have constants, 2 and 1 will be constants, and then we'll have the variable x. So let's draw what that would look like as a tree. Start with plus. And plus is an operation that has 2 children. So one child will be the constant 2. And then the next child will be the minus operation with children constant 1 and variable x. Right? So this is a tree representation of our language, of our equation. So why is this useful? So the tree is useful for a few different things. One, we want to be able to execute the program with the tree if we wanted to. That's sort of what an interpreter does. And you can execute this by walking the tree. So we want to be able to execute. We want to be able to output the tree in some form. And so you could really easily output the source code back again if you walk the tree. So you want to be able to output things. And depending how you walk the tree, you could output different languages or machine instructions, whatever you want. And then we also want to be able to manipulate the tree. And we can do that to perform optimizations. So an example of that, let's say that this was not an X. Let's say that it was the number 1. Right, so in our tree, we've got the number 1. Right, so someone might write something like this in the source code of a language. And you notice everything is constants here, right? So if we're executing this, if we're walking the tree and executing this, we're doing a lot of work that we don't actually need to do, right? We could optimize away these constants ahead of time. So we could do a constant folding manipulation where we recursively traverse the tree, right? And so we look at this node and we say, okay, both of its children are constants. So let's go ahead and perform the subtraction operation, 1 minus 1. So we can get rid of these nodes. And this just becomes a 0. And then again, since we're doing it recursively, we look at the plus and we say, okay, both of these children are constants now. So we can go ahead and do that operation too. So we can then erase this. And it just becomes a 2, right? So we've optimized our tree down to a single constant, and now we can execute it very fast. So that's the basic idea behind an abstract syntax tree. So how do we actually implement one? Well, it turns out that's really easy to do. At least with a simple language, it's easy to do. So I'm going to implement this in F#, just because you can do this kind of thing really concisely in F#. And we're going to use sum types or discriminated unions. And so if you have not seen already the video about algebraic data types, if you watch that first, this might make a little more sense, but I'll explain a bit as I go along. So in our language, our nodes, and I'll call them AST nodes, could be one of 4 things. We're going to support addition and subtraction. So we're going to have 4 different kinds of nodes. We can have an add node. Oh, Visual Studio is correcting me. Let's turn that off. I recommend everyone who uses Visual Studio report this as a bug. Toggle completion mode does not persist. When you close Visual Studio and open it back up, it goes back to the wrong setting. All right, so AST nodes can be an add operation, a subtract operation. They can be our variable x, or they can be a constant. All right, so each of these different types contain different data. So an add operation needs to have its 2 children, right? So we're going to say this can be add consists of 2 children AST nodes, right? So it's a recursive definition. And subtract also has 2 AST node children. X does not have any data associated with it. And then constants will do just integers. So a constant will have an integer inside. And if you were implementing this in something like C++ or C# or Java, you could do a very similar thing here by having an abstract class AST node, and then subclasses add, sub, x, and constant that contain the necessary data. All right, so that's basically our type for AST nodes. That's all we need. But now we need some operations on it. So one of the things we talked about we wanted to do was be able to execute our language. So let's make a function that can evaluate an AST node. So this will take in a node, and we have our variable x. So we need to evaluate things in terms of x. So we also need an x. And we're going to use pattern matching, which is like a switch statement in other languages. And we'll do a different thing in each case, right? So add, subtract, x, or constant. All the different cases. And this is a recursive operation, right? And that can make things easy to think about. Maybe we don't know what to do with add and sub yet, but with a constant, how do we evaluate a constant? Well, that's really easy. So the constant has an int inside, so we can extract that int like that into the variable v. And all we got to do is return the variable v. That will be an integer, and we return it. In the case of x, well, we're evaluating in terms of x. So in the case of x, it's also easy. We just return whatever x was supplied to the evaluate function. And now for add and sub, so we can't just add. Well, we get out of these. We've got to get our left and right nodes out of add and sub like this. This is just a tuple, which is like a struct with two things in it. We just haven't named them. So we can extract the left and right like so. But we can't just do L plus R, because L and R are AST nodes. But we can get the value of an AST node by calling evaluate on it, right? So, and we'll pass X down the tree. This should be L plus evaluate R. Right, so we evaluate the left, we evaluate the right. Those will eventually return an integer once they hit a constant or X, and then we add them together. And then we do the exact same thing with subtract. And that's it, right? We have now implemented an interpreter that can interpret our very simple language. Let's give it a try. So let's make, what was our example before? 2 plus 1 minus 1. Well, let's start with 2 plus 1 minus x. So we'll do add constant 2, and then sub constant 1 x. Are we good? Yeah, I think that's it. Okay, so that's our equation. And we want to evaluate it, so let's say let result equals evaluate equation. And we need to supply our x, so let's just say x is 1. So we should get 1 minus 1 is 0, 2 plus 0 is 2. We're just going to print that to the screen. And we'll read from the console, just pause. And there we go. We get 2. And we can make this more complicated. Do another add. Add 5 to 2, so we should get 7. There we go. All right, so we have an interpreter for our AST. One of the other things we need to be able to do is output. So let's do that. So let's make a function that will turn our AST into a string. And again, we're going to do a match and handle each case. Okay, so to print out a constant, we just need to cast our integer to a string. So that's easy. And then for x, we're just going to print the string x. And then for subtract and add, we're going to wrap them in parens, because we're not going to deal with order operations right now, so everything will be in parens, so it's clear. And then we will do, again, recursive AST to string on the left side. And then we're doing minus. And AST to string of the right side. And we need to say that this is going to be a recursive function. F# makes you declare that explicitly. And the same thing will be done for plus, but with the plus operation. And that's all it takes. So let's give it a try. Equals AST to string equation. So now we're going to take our equation, turn it to a string, print it out. There we go. 5 plus 2 plus 1 minus x. And we can really easily output this in different forms, right? Like if you wanted to output Lisp instead, you can move the plus over here, like so. And just have this be a space. Move the minus over here, have this be a space. And now you have a Lisp-like syntax. Okay, so final step though, the final reason for using a tree to represent your language is the ability to manipulate it. We talked about constant folding, so let's go ahead and implement that. We'll do, we'll make an optimization pass on our AST. So we'll call that constant folding. It'll take in a node. Once again, we match on each case. Okay, so if we have a constant, then all we need to do is just return the same thing. Right? A constant's already a constant, so we're done. If we have a variable, then there's definitely definitely not a constant. So we just return x again. But when we have add and subtract, that's when things get fun. In this case, what we want to know is, are the left and right themselves constant? And we need to figure that out recursively, right? Because the left side of add might be another add, but if the two children of that add are constants, then we can add them and it will become a constant. So we need to recursively constant fold and see if the result of the recursion is a constant. So we're going to match on the function call constant folding of L and the constant folding of R. Like so. Right, so we're matching on a tuple. And if both results are themselves constants, right? So if the result of this recursive call, if they're both constants, then we're going to extract the value of each constant and return a new constant with those values added together, because this is add. Now the other possibility is that they are not constant. In that case, we just want the new L and R right, we're going to extract the left node and the right node because they're not both constants, and return an add node with those, the new L and R. And same thing for subtract, except we will subtract in the case of them both being constants and return a new subnode. We need to match up our indentation. Okay, so now in this case, let's see what this equation is again. So this is not going to have any constants that can be folded. So let's test that and make sure it's not changed. So we have our equation. Optimized equation equals constant folding of EQ. Let's get the output of the optimized equation and let's print it. Okay, that's the same because it couldn't find any constants to optimize away. Now if we change this x to constant 2, then we should see the whole thing optimize away, and it should be the same as the evaluation of the original equation. So we can test that. We can say the result will be the evaluation. In terms of 1, there are no x's, so that won't even matter. And then we'll get the optimized equation, which should be a single constant. And we'll print out both. So folded equation, evaluated equation, those should be equal. There you go. 6 and 6. So we have now built, we got more stuff than we need there. We've built an abstract syntax tree. We've built an interpreter for it. We've built a transpiler of sorts. We can output our AST as some language. And we have built an optimization pass, constant folding, which will figure out any constants in the tree and shrink them down. We've done all of that in just 32 lines of code, built an optimized interpreter with an AST. That's how simple it is. And of course, if you were implementing an actual normal programming language, you would have to also account for things like if statements, multiple expressions in a body, while loops, and so on. So this will get much more complicated than the simple example here, but this gives you enough of a starting point to start figuring out how you can do those kinds of things. Like once this clicks, it's not too hard to go from here to making more and more complex languages of your own. And I encourage you to play around with this and give it a try. See if you can add conditional statements to this, or real variables to this, or loops to this. That's kind of a fun exercise. All right, that's it for now. Thank you for tuning in.